The focus of this lesson is models for population growth. Our focus is the law of natural or exponential growth, and it is expressed mathematically by the differential equation dp dt is k times p, where k is a constant and p represents the population. What this model says is that any population growth in any sort of population, whether it be people or bacteria or foxes or whatever, is represented by some constant times the population itself. So for example, in the image we see here, we can see that the population is growing by double, right, each time. So we go from 1 to 2 to 4 to 8 and so on. And thus in this situation, our constant is 2. Okay, now we're going to be using this model to help us solve some differential equations. Example 1. The rate at which a population of fruit flies grows is assumed to be proportional to the number present. Suppose there are 100 fruit flies initially, and after 3 days there are 200. Find an expression for the number of fruit flies in the population at time t greater than or equal to 0. Whenever I get one of these population problems, I'm always going to start with the same model we know to be true. So dp dt is equal to k times my population. Now, ultimately, I want to solve this equation and get a function that represents the population. So I'm going to separate my variables. I get 1 over p dp is equal to k dt. Now I'm going to integrate both sides, and I'm going to be left with ln, absolute value of p plus a constant, and k times t plus a constant. Then I'm going to join my constants. So I have ln of absolute value of p is equal to k times t plus some new constant. Then I'm going to do base e exponential on both sides, and I'm going to be left with absolute value of p is equal to e to the kt times e to my constant. Now, population can't be negative, so I'm going to remove the absolute value, and I have p is equal to, and then note here, this e to a constant is just a constant, so I'm going to move that constant that I see right here, I'm going to move it out to the front and just call it c, and then e to the kt. So this here is my generic model for population growth based on this initial differential equation. Now, once I have that, I'm going to identify my constants, my big C and my K, using the information that was provided in the problem. Now, the problem does tell me that there are 100 fruit flies initially. That is, the population at day 0 is CE to the K times 0 is 100 fruit flies. I know that k times 0 is 0, so e to the 0 is 1, so I have c times 1 is 100, or c is equal to 100. So my model is currently p of t is equal to 100 e to the kt. Now from here, they gave me more information. They told me that at 3 days, we're at 200. So let's take that information and plug that in. So the population at 3 days would be 100 e to the k times 3 is 200. Now we're going to solve this exponential equation. Let's start by dividing both sides by 100, and we get e to the 3k is 2. We'll take the natural log of both sides, so we're left with 3k is ln of 2, and then let's divide both sides by 3. So we get k is equal to 1/3 ln of 2. Now we're going to take that information and plug it back in to the original equation for k. So we're left with p of t is equal to 100 e to the 1/3 ln of 2 times t. Now rearranging this, we can actually see that we can clean this up a bit. So we have 100 e to the ln of 2, and then let's move that t and 1/3 to the outside, because e to the ln of 2 is in fact just 2. So we have 100 times 2 to the power of t over 3, and this here is our population model. Now, when you look at it, it very much makes sense. So we see our 100 being our initial population, and we see times 2, meaning it doubles every t over 3. That is every 3 days. So when I plug in 0, I get 100 times 2 to the 0 over 3, or 100 times 2 to the 0, which is 100 times 1. Whereas when I plug in 3 days, I get 100 times 2 to the 3 divided by 3, or 100 times 2 to the first power, which would be 200. And it's always good to stop and verify that your model works. Now for the second part. When will there be 1,000 fruit flies in the population? Now note, this here models the population. So the question is, when will P of t be 1,000? So we'll set that equal to P of t. So 1,000 is equal to 100 times 2 to the power of 2t over 3. And now we're going to algebraically solve this. So let's divide both sides by 100. And we get 10 is equal to 2t 2 to the power of t over 3. Then we need to get rid of the base 2. So let's ln of both sides. So we have ln of 10, and then we have ln of 2 to the power of t over 3. When we have the natural log, powers drop out front. So we have t over 3, ln of 2, and we have ln of 10. Then we'll move the ln of 2 to the other side. So we have ln of 10 over ln of 2 is equal to t over 3. Then we need to get t by itself, so we'll multiply both sides by 3. So we'll get here that t is equal to 3 times ln of 10 over ln of 2. And then we'll type this in a calculator. All right, so we have 3 times ln of 10 over ln of 2. And we get here 9.966. So t equals 9.966 days. So about 10 days.